Can you see my screen?
Yes, ma'am.
Yes, ma'am.
Okay. So the first question is, I've given you a grammar S going where the productions are S going to ASB, BSA, or SS or epsilon. What is the language that this grammar is generating?
Ma'am, strings having same number of A's and B's.
Okay, so L of G, the claim is all strings where with number of A x is equal to number of bx. How will you prove this?
Ma'am, we have to prove that for all strings that are derivable from S, this property holds, and for all strings that for which this property holds, it is derivable from S.
Okay, so let's first suppose that I am saying S derives some x. Then show that hash ax is equal to hash bx. How will you show this?
Induction on length on S.
Induction on length of derivation.
X.
Length of x, okay.
Yes, ma'am. Derivation also.
Which one? Also or it can't be also, right?
Ma'am, shouldn't either of them give two separate valid proofs?
Yeah, shouldn't either of them give separate proofs?
Yes, ma'am. Both valid.
Okay, so if you are inducting on the length of x, can you give me a proof? Suppose I induct on the length of x. There might be one. What will be the proof?
Ma'am, if length of x, if x is epsilon, then it's trivially true.
Okay.
Otherwise, if x ends with a, or x starts with a and ends with b, or x starts with b and ends with a, then it is also true
Why?
because of the second and third clause of the production.
So you're saying, so you have to prove something about x1, right?
Yes, ma'am. In x1, the number of a's is one less than number
Okay.
of a's.
So then there must be some derivation from s to x1 as well. So how are you deriving after that?
Ma'am, then we can assume that both of the characters same, and the first character and the last character of the string are same, and then we can define the surplus variable, and then we can just
No, 1 minute. So you have A, X1, B, and from the structure, you know that, uh, yeah, what do you know about X1? How do you know that X1 will have this property?
a of x1 is 1 minus a of x, and b of x1 is 1 sorry, a of x1 is a of x minus 1, and b of x1 is b of x minus 1.
Yeah, but you don't know whether X has this property, right? X is just something that I have derived. You have to prove that it has this property.
Ma'am, then x1 is shorter than x in length, so x1 by induction hypothesis holds this property.
But x1, I don't know whether x1 is derived from S, right? I don't know whether x1 is part of the grammar.
Okay, ma'am. So this can be also derived from the SS rule. Okay.
But I don't know what the previous step, I don't know how I got to AX1B. So therefore, I think at some point you will
Yes,
have
ma'am,
to
yes.
use the fact that that you have to induct on the length of the derivation. Okay, so if I induct on the length of the derivation, then how will you do it? So suppose you have I will say that at some point you have alpha, and then in one step you are going to x, right? Now, how will you do this? What can, so in one step, what will alpha be? Alpha will be of some kind, alpha can be one of the three kinds, right? It will be x1, s, x2, and this s gets replaced. Or, okay, I think you need to generalize further. You take a sentential form and you show that the number of a's in the sentential form is equal to the number of b's in the sentential form. So let me just write it this way. Suppose I derive b in n plus 1 steps. I will show that the number of a's in beta is same as the number of b's in beta. So if look at beta, alpha can be of the form some alpha 1 s alpha 2, and then beta will be of the form either alpha 1 a s b alpha 2 or alpha 1 b s a alpha 2 or alpha 1 SS alpha 2 or alpha 1 alpha 2. So now notice that on alpha you can apply the induction hypothesis and say that number of A's in alpha is equal to number of B's in alpha. Number of B's in alpha. So now if you look at this first thing in beta, the number of newly introduced A's and B's are equal. So then in beta as well, number of A's in beta is equal to number of B's in beta. Similarly, in this rule also, number of newly introduced A's and B's is the same. Here and here, we are not introducing any new A's and B's. Therefore, this condition holds, and therefore we have been able to show that any sentential form that is derived from S has a number of A's equal to number of B's. So in particular, any sentence will also have number of A's equal to number of B's. Okay, now in the other opposite direction, suppose you have suppose I take an x such that number of A's in x is equal to number of B's in x. How can I show that? Let me just write it as show that S derives x. How will you do this? Can you tell me what can be the form of x if this happens? So I think you were mentioning something about surplus function.
Yes, ma'am. We can consider the surplus functions of all the prefix of x.
So here surplus function of let me say y is number of A's minus number of B's?
Yes, ma'am.
Okay, now what are you doing?
Ma'am, if the surplus function is never zero except for the empty prefix, then it has to be the case that the first letter and the last letter are different.
1 minute. If for no proper prefix S of y is or rather if for all S of y is strictly greater than 0, then x, you're saying x will be of the form ax1b or bx1a. Is this what you're saying?
Yes, ma'am.
Okay. And otherwise, there exists proper, okay, I will also say proper where y is not equal to epsilon. Epsilon we don't have to consider. Proper prefix y not equal to epsilon with sy equal to 0. We know that Sx is equal to 0. Therefore, x is of the form yz such that Sz is equal to 0. Now, what will you do?
Ma'am, this can be sy less than 0 in the first case as well, right?
Sy less than
Strictly
0.
less than 0 for all of the
Yes, ma'am.
prefixes.
Yeah, sure. It could be sy less than 0. There will be another case with sy strictly less than 0.
Like the greater than 0 will go to ax1b and the less than 0 will go to bx1a.
Right. So I think it will be this. So basically, I think I should say sy is not equal to 0. Anyway, this is the structure that you're going to get. And then if I have ax1 b x1, I know that x1, again from the structure x1, in this case x1 is going to have the same property. Number of ays is equal to number of by's. So I can derive x as follows. S going to ASB, which after some time goes to AX1B, and then this is equal to X. And similarly BX1A. And over here, if X is equal to YZ, then and Y and Z have the same property, then just inducting on the length of the strings, I can say that S goes to SS, and then after some time it goes to YS and then YZ, which is equal to X. Okay? Okay, so now the next question, the next extension is what happens if I want a CFG for all strings where number of A's is greater than equal to number of B's. Then can you construct a CFG?
Ma'am, along with the previous production, can we add another production saying P goes from P goes to AP or AS?
Then you have SS and then
Epsilon.
epsilon
and then we have another production P, which
P.
no ma'am, separate.
Huh?
Ma'am, S does not go to P.
Oh, okay.
P goes to AS or AP, and P is the start symbol.
Okay, P is the start symbol. Then let me write it separately. Let me write this as E. And then I'm writing this as S, and this is AS or AE or
Or epsilon. Sorry, or E.
or E.
Ma'am, the AE is not required.
AE is not required. Okay. Okay, why are you giving this? So E, I'm assuming, is all the strings that you're generating where everything is equal. The surplus is 0.
Yes, ma'am.
Okay, so can you tell me why you are getting this? I don't think that's what you
No, ma'am,
meant, because you have S going to E. Okay, no. So you tell me why you said
No, ma'am,
this.
it still contains some string which cannot be generated.
Yeah, so how about if we do this AS let me see. Yeah, how about if we do this? So the idea is E will be strings which have same number of A's and B's, and S is sort of introducing the surplus. So either if I'm starting a string with A, I could have the rest of the strings. So suppose my X is equal to AX1. It is possible that X1 could have a positive surplus. It is also possible that X1 could be equal, could have zero surplus. And otherwise, if I'm starting with B, okay, so is it possible that X1 has negative surplus?
This thing will accept BBA, right?
Which one?
This whole thing, like ENS. We start with S and then we do BS twice and then
BB.
S and
Oh, yeah. It's accepting BB.
BB.
Right. Okay, so any other suggestions? Or whoever suggested this, is there any, can you change this in any way? Because I see your logic, but we haven't completed this yet. Again, if you consider the surplus function, then what can X and if you consider X starting with A and starting with B, then what is the property of X1? Can somebody tell me what is the surplus going to be for X1 in each case? What are the possibilities of surplus?
And in the first case, a minus b would be greater than equal to -1 for x1, and then surplus would be greater than or equal to 1 in the second case.
You're saying number of AX minus number of BX is
Greater than equal to -1.
greater than equal to -1. And over here, number of AX minus number of BX is greater than equal to 0.
Greater than equal to 1.
Greater than equal to 1, right. Greater than equal to 1. Okay, so if I have something starting from, let's go along with this idea for a little bit more, then I can give you another one. I can give you another grammar. So basically, what I want is I want this this production to produce strings which have equal number of A's and B's. And now with S, I want to introduce the surplus. Now, if I have B, then I know for sure that I need a surplus in the rest of the string, right?
Yes, ma'am.
Okay. Now, if I have X and I have surplus of 0, okay, if I have a surplus
Ma'am,
huh?
can we do something like S goes to ASB, BSA, SS, and epsilon, just like E, and then we can
ASB, BSA, SS, epsilon, and then
AE.
AE.
Yes, ma'am.
Okay, and then what is E? Oh, E is this.
Yes, ma'am.
Okay, let me see. Oh, what's the logic over here? What are you trying to capture with this?
We can produce a string of type number of a's greater than equal to number of b's from an existing string of number of a's greater than equal to number of b's, the same way we did a number of a's equal to number of b's, and we just add one production that adds the surplus to the string.
Once more, you have ASB. This is producing the number of strings.
Ma'am,
So this
Only-
S is producing the surplus.
Yes, ma'am.
If
Let's say
required.
initially we will obviously add the surplus of 0. Then we will be for the first 4 we just keep the surplus the same, and whenever we need the surplus to be greater, we just go to AE, and that
Correct.
adds the surplus.
Okay.
And yeah, that's what it does. Like if we have how many times we do the SS thing, that will determine how much surplus we extend for the AE part.
But if you just have AE, then you can add at most one surplus, right? You cannot repeat this.
Ma'am, we have the SS thing, right? So the number of S in the whole thing will increase as well.
No, but then you have to prove more stuff. Then you have to prove that you can break such, if you have surplus more than something, then you have to prove that it will be of structure SS. Okay, so please try to figure. I think this will work out because logically it seems correct, but for for the sake of time, I'm just going to give you one thing. This is a correct grammar for the language. And using similar techniques, you can prove that this is correct. Okay, but this logic is also, I mean, try to work on this, because this can generalize many other problems of similar form. Okay. So try to prove in a very similar way. You can prove that this is a correct grammar for the language, and you also try to prove like this. Okay, so let's move on to the next question. Next question is CFG. Okay, I will again, let's do the first step, and then it comes to a problem which is similar to the previous thing. How will you solve this? If you have a CFG for X such that number of A's is not equal to number of B's, how will you solve this problem? What does this mean? What does this language, what are the strings that are in this language?
And the surplus will be non-zero.
S of X is not equal to 0. So again, I will write it as S of X is strictly greater than 0 or strictly less than 0. Okay, so again, the problem comes down to, let me just write it down as this. This, in terms of the structure of the string, means number of A's in X is strictly greater than number of B's in X, union all X's such that number of A's in X are strictly less than number of B's in X. Okay, so again, now this problem is very similar. So try similar techniques as before and try to see that both these languages, L1 and L2, are context-free grammar, context-free languages, and we know that the union of context-free languages is also a context-free language. Okay, so this I'll leave it to you. Again, both these exercises, whatever we have left, very similar to the first exercise that we solved. Okay, so let's move on to the next one. So context-free grammar for A to the M, B to the N, where M is less than equal to 2 to the N. Sorry, M is less than equal to 2N. So basically for every B introduced, we know that at most 2 A's can be introduced.
Ma'am, S goes to ASB or AASB or epsilon?
AASB or epsilon. I think you're missing one thing.
SB will be there.
Right. SB will be there. Why are you saying, okay, what is your logic?
Ma'am, for every B, we introduced at most 2 A's, and for strings without A's, the last production SB will.
Okay. Right. So all strings in A to the M, B to the N will be of the form either there is no A, which means it's only some B to the N, or for every B introduced, you can introduce at most 2 A's. So therefore, either ASB or AASB repeated many times will give you the string that you're looking for. Okay. B, not of A to the N, B to the N. So we know that A to the N, B to the N is a context-free language. Now we want to see whether not of A to the N, B to the N is also a context-free language. Notice that context-free languages are not necessarily closed under complementation. So what are the kinds of strings that are there in this language? So let me just write it as L1. So L1 could be all the strings A to the N, B to the M such that N is not equal to M. And what are the other strings that are there?
Ma'am, we can have something of the form U B A V, where U and B are strings.
X is equal to U, B, A, not exactly
UB.
this, U1, right, like this, right? Is this what you meant?
And aren't they the same?
Yes, ma'am. If this can be also written as U1
UB.
BA.
Yes, ma'am. If there is B and then somewhere later there is A, there will be a BA somewhere in between.
Is that true? 1 minute. Yeah, okay, sure.
In between, we'll have to put something, right?
Yeah,
If
yeah,
A,
yeah. So you're just looking at where the first alteration is happening.
yes, ma'am.
Okay, good. Yeah. Okay, so can you quickly give me context-free grammars for these two? See, L2, first of all, notice that this is actually this is actually a regular language, right? You just have to detect this pattern.
Yes, ma'am.
Okay, so this is regular. What about this? How will you show that N is not equal to M? See, always in these cases, keep breaking this. L1 is equal to L1 dash union L11 union L12, where L11 is basically N greater than M and L12 is N less than M. Okay, so for N greater than M, what grammar will it be? So A to the N, B to the M, such that N is greater than M. What will it be? You have to introduce more A's basically. There will be more A's and after that it will be equal. So what will it be?
It will be ASB or A.
Or A, you can introduce many more A's.
Yes, ma'am.
Or AS.
Correct. Or
AS.
AS or epsilon. Oh, no. I don't think
Epsilon
there
won't.
can be
Ma'am, not
epsilon.
epsilon.
No. Yeah, not epsilon. Because there has to be at least one A since we are greater than, N is greater than M. Okay, and
Ma'am,
similar.
to get
S
rid of
should
that
also
S,
get
will
to A.
yes, ma'am. It needs to
Into
get to
A.
A.
Right. A. Right. And this will parallelly you will do it for B. You will have to add more B's at the end. Okay, and since L is equal to L1 union L2, and I showed that L1 is the union of two context-free languages. So L1 is a context-free language, L2 is a regular language. We know that regular languages are context-free languages. So L2 is also a context-free language. Therefore, the union of the two is a context-free language. And therefore, the complementation of A to the N, B to the N, as well as A to the N, B to the N itself are both context-free languages. Okay. So now let's come to some problems where we have to show that some some language is not a CFL. So Bn is the binary representation of a decimal number n. And you have to show that Bn hash Bn plus 1. So this is a string where the symbols are, where the alphabet is 0, 1, or this special hash symbol where hash appears exactly once to separate out Bn and Bn plus 1. So you have to show that Bn hash Bn plus 1 such that n is obviously greater than or equal to 0 is not a context-free language. But if I do Bn reverse hash Bn plus 1, then it is a context-free language. So obviously, before we get into the problem, we have to analyze what Bn looks like for an n, and what Bn and how Bn and Bn plus 1 are related. So Bn can be of two forms, right? It could be 1 to the, let me not write it as n, could be 1 to the k, or it can be some 1 and then let's say it has some w, it has some 0, and then let's say it has some 1 to the k. This w could be empty. So if it's 1 to the k, then what is Bn plus 1?
1 0 to the K.
1 0 to the k. And if it's this form, then
1 W 1 0 to the K.
1 w 1 yeah, that's not interesting. Let me do the other one. 1 w, no, this yeah, right, this was the interest. Yeah, so what did you say? What will this be? 1 w 1 0 to the k. And notice that these are the only two forms. Either you will have at least 1 0 in the string. Look at the rightmost 0. That is where the flip is going to happen. Okay, now, so basically Bn plus 1 will either be of the form 1 to the k hash 1 0 to the k, or 1 w 0 1 to the k hash Bn, right? So 1 w 1 0 to the k. Okay, now you have to show that this is not a context-free language. So one standard way of doing it is applying pumping lemma. How do you want to do it? What is the, so let me say the pumping lemma constant. Let's say this is k. Now you have to choose a string of length at least k, right? Z such that length of z is at least k. Okay, now proceed. How will you apply pumping lemma? What is the z you want to choose? And then you have to analyze what happens when the adversary gives you a 5 partitioning of z. Okay, so did you get time to go through pumping lemma, or did you get time to go through the last lecture? Because otherwise there's no point in solving these problems now. We can solve it later. We'll just directly solve B. Let me know, then we can delay it for the next tutorial. So what Z will you choose then? Okay, let me give you the Z maybe then. So let me choose Z as 1, 0, 1 to the, no, let me try a little bit more. 1, 0 to the 2k, 1 to the k, and this will be 1, 0, 2k minus 1, 1, 0 to the k. Okay, now you have to argue that for all u, v, w, u, v, w, x, y such that vx not equal to epsilon and length of vwx less than equal to k, there exists I such that u v to the I w x to the I y does not belong to this language. I'll call it L. So how will you argue this?
Ma'am, the symbol hash has to belong to W because
What happens otherwise?
otherwise, if the symbol hash cannot belong to V or X because then by the pumping lemma we can have multiple occurrences of hashes if we pump in.
But what if VWX belongs completely over here or completely over
Yes,
here?
ma'am. Then one of the representation U completely contains Bn or Y completely contains Bn plus 1, but the other one is changing, so that won't be the predecessor successor relation anymore.
Right. So if VWX is completely contained in Bn or Bn plus 1, then the bitwise, there is a bitwise contradiction. Because if you just pick I to be equal to, let's say, 3, then the number of bits on the before hash is becoming much greater than the number of bits after. I think you either take I to be equal to 0. Let me see. You take I to be equal to 0 in the first case where it is in Bn, and if it's in Bn plus 1, you take I to be equal to 2, just take 3. Okay, and then on the left hand side and the right hand side, notice that the difference in bits can be at most 1. But if I do this, then the number of difference in the number of bits before hash and after hash becomes more than 1, and that means that it cannot be a relation between n and n plus 1. So that this case is handled. Okay. Next is, you're saying it must be that V and X on either side of hash, because otherwise if I pump up, then I will introduce more hashes and that will just violate the form of the strings. Okay, so now what happens? Now, if V and X has to be on either side of hash, then because of the length, I know that V is of the form 1 to the L and X could be of the form what's on this side? Yeah, X could be of the form 1, 0 to the power L2 or 0 to the power L2. These are the two things that X could be of, right? Because I have enough zeros here so that X cannot go into this portion. Okay, so now what happens if what's the I that you're picking? That will lead to a contradiction. Okay, so one thing is if I pump things out, if I put I equal to 0 in this case, then again structurally it's not possible, right? Because I've removed the one which is following the hash. So structurally this is not possible. What about this case? What will be the I?
We can put I equal to 0 and then the difference will not be 1 for the numbers.
Right. If I pump these things out, then notice that the structure, the left hand side and right hand side will not be the binary representations of n and n plus 1. If you look at the last 0 and the last 1 and the last 0 in the left hand side and the right hand side, then they will not match in the correct places. Okay, so by pumping lemma we showed that the first language is not a context free language. What about the second language? So notice that for Bn reverse hash Bn plus 1 is going to be of the form either 1 to the k hash 1 0 to the k, or it will be 1 to the k 0 w reverse 1 hash 1 w 1 0 to the k. Okay, so what will you do?
For the first part, we make a context free language like S maps to 1 S0 or hash 1.
And here, let's call this S1. And here, I think 1S0 will still be the same. What are you doing? What will you do here? So up to a certain point, it's the opposite of each other. Then it becomes the same thing. And then there is the hash.
We can add another state. Let's say
Okay, so here, yeah, okay. You can
we
add
can
another state.
add another state. Let's say E.
Can you
This
just
goes to
add
like
E, or will you have to
0
have a
E1,
0E1?
and then E will obviously go to
1E1.
1E1 or 0E0 or hash.
Okay, so this is correct. Let me just check this part. 1S0. Okay, so you start with 1S0. Then at some point you go to 0E1. Okay, and then from E you start replicating up to here. 0. I think you need to put 1 hash 1. Because this has to be 1, right? It can't be 0.
Yes.
Yeah. Okay. Okay, so and then you find, to get the language, you have S going to S1 or S2. Okay, so quickly, one last thing. Let L be a context-free language, then prove whether this is true or false. WW, such that W is in L, is also a context-free language. True or false?
Yes, ma'am. True, ma'am. We can just add another production S prime equal to SS.
Why will it give the same W? It can give another W, right?
Yes, ma'am. Yes, ma'am.
But I think we've already done this in class. So if you take L to be AB star, so then this is a regular language. So this is a context-free language. Now what did we do in class? WW belonging to AB star. Yeah, WW belonging to AB star is not context-free. Right? We did this example in class.
Yes, ma'am.
Okay, so what about B? In B, you have to show that if WW belongs to L, L being a context-free language, then you have to prove whether it's true or false that the set of strings W will also be context-free. So for the sake of time, I'm saying this is false. Now, how will you do it? And I'm also giving you the hint that A to the N, B to the N, C to the N, such that N is greater than or equal to 0. This is not context free. Similar argument as A to the N, B to the N, A to the N. You can show the same thing. We've seen that A to the N, B to the N, A to the N is not context free by pumping lemma. Using similar pumping, we can, using similar strategy, we can show that A to the N, B to the N, C to the N is also not context free. But L has to be context free. Okay, so let me just give you this language. I'm saying L is equal to A to the I, B to the I, C to the J, A to the J, B to the L, C to the L. And I'm saying I, J, K, let's say are all greater than equal to 0. So if I have, can you complete the proof from here? So I notice that this is going to be context free. So just give a production like A1, A2, A3. And then each of A1, like A1 is going to generate A, S, B. Sorry. A, A1, B, or epsilon. A2 is going to be C, A2, A or epsilon. A3 is going to be B, A3, C or epsilon. Right, so this is, you can generate this. You just break these things up into parts and generate them separately. But what is WW in this language? If there is a string of the form WW in this language, what is it of the, what can you say about IJ and L?
All three must be equal.
Right, WW will be of the form A to the I, B to the I, C to the I, A to the I, B to the I, C to the I, which means W will be of the form A to the I, B to the I, C to the I. And this we know is not context free. Okay? Okay, so we had one problem left, but we can do it later. Otherwise, we have more or less completed. But there were some similar kinds of problems that you can try on your own. We saw what happens when number of A's is equal to number of B's, and it's left as an exercise. What happens if number of A's is greater than equal to number of B's, and what happens if number of A's is strictly greater than number of B's. Okay. So we will send an email to you today, sometime today, about the logistics of the test on Tuesday.